Say that again.
Like if I left with +1 minus 5/4.
I would want you to simplify that. So I'd want you to do 1, yeah, so 4/4 minus 5/4. Negative 1. Yeah, so. Okay, but yeah, like e to the 4th, there's just nothing we can do with that. So this one's just a basic antiderivative, and then you plug in your, or did we have to split that up, I think? The original problem, wasn't it? Yeah, we had to. Yeah, you had to split it up. So you get 5x cubed plus 1 over x, yeah. So we split it up, and then we just do a basic antiderivative, plug in our e, plug in our 1, okay? And so you get that. Okay, number 9, that was kind of a disguised integration by parts a little bit. Most of the time, we're going to be doing integration by parts with ones like I put over here, like x e to the x. That might be 2x, it might be e to the 3x, or this might be ln 4x or something, you know. But e to the x times ln x or sine x times x or something. I mean, for sure, you're going to see that, right? For sure, you're going to see what I would call just a very basic, routine integration by parts. But then there also might be one, if there's another one, that's a little more disguised, where like this one. I mean, because this one, when it's a fraction like that, that's when you might think, like Skyler, we were talking to this morning, that you let u be the bottom. Well, the reason you wouldn't let u be the bottom here is if you let u equal 2x, the du is, or excuse me, if you let u equal x squared, the du is 2x dx, and that's not sitting there. And then you got this natural log sitting there with nothing to do with it. So that's why you wouldn't let u be the bottom in that one. You wouldn't let u be the ln x because the du would be 1 over x dx. And so if this was just an x down here, and actually that's what we did this morning, right? We had ln x over just plain old x. Well, then you could let u be ln x. The du is 1 over x dx sitting right there. That'd be a great idea. But in this case, it's x squared, so that doesn't help us. So the thought is bring up this x squared as x to the negative 2, and now it looks more like one of those integration by parts ones. We got a log, we got an algebra, we got a mixture of those two things. Then it looks like that'd be a good way to go. Okay, so we let u be the log for the ate, we let dv be the x to the negative 2, so we do the antiderivative of that, do the du of that. And so when we do u times v, that's this part, minus the integral of v du. So if you look at that, du, this is x to the negative 1. And you take that times v, which is negative x to the negative 1. That'd be negative x to the negative 2. Whoops, x to the negative 1. So you'd add those powers. And then that's just a power rule. So raise that up to negative 1, divide by negative 1. Those negatives would cancel, so you still have this minus here. Okay, number 10 is that one with the arctangent. It said 1 plus 4x squared, but I think we talked about that a little bit. That's the same as that, so you'd want to let u equal that right there. If there'd have been an x on top, then you could have let u be the whole bottom. You could have let u be 1 plus 4x squared, because then you got 8x dx. You'd have had an x dx up on top that could have subbed out, but there wasn't one, so that's when you start thinking about arctangents.
Like the little scribbled thing here.
Yeah, I think for some reason I had a squared there. And then I hand wrote these out, and then I scanned it, and then I realized I had a mistake, and then I had to get that out of there. It was scanned as a PDF, so I put it. So that's pretty good. So anyway. And then this one, and then this is a good u substitution, again, because there's stuff on the inside, and the reason that makes it a really good u substitution, when you let u be that thing on the inside, the du is sitting right there. The derivative is 6x squared. Oh, good, there's an x squared right there. So we move the 6 out of the way, and then x squared dx. Okay. All right, how about any others that you tried or saw in the book that were troublesome?
It was 1 over 9 plus x squared dx.
Say that again.
1 over 9 x squared dx. Is that like arctangent?
Yeah, remember the one I did yesterday? It was just like this, but it had a 16 here. And I think I said I wasn't gonna do that to you. I was gonna, what I was gonna have you do would be more like this one, right? We had one, where you had the one here. And it just because I have to pick and choose about what I'm going to emphasize. I mean, we certainly could do this one, but what you do on that one is you take the bottom, and what do we say to do? Was this on?
Squares one where you made it?
This is one of those practice tests, right? What did we say to do with this? Remember? It's going to be an arctangent. You need a 1. How can you get a 1? You don't remember? We did this exact problem yesterday, except we had it. Right. So we factor out a 9 out of the bottom. It'd be 9 plus, it'd be 9 times the quantity 1 plus 1/9. And then this we would rewrite, so we bring the 1/9 out, this 9, and right, we bring that out. And then this would be 1 plus the quantity 1/3 x squared. Right? So all I've done is just rearrange algebraically that. Now what are you going to let your u be? 1/3 x. Right? And then you would just do a u substitute from there. It's going to end up being an arctangent. So anytime you see, I mean, we've done enough on it now. Maybe we should put it on. That's going to be our thing. So if you do those practice tests on that Jacksonville site, they do. It seems like every one of them has one of those. It's the same thing every time. But we probably won't do that. But I might give you, and I usually don't do 1/9. I usually stay away from fractions. But like I said, I give you one like that. That was what we did yesterday. Right? You got to recognize that this would be the same as 2x quantity squared. So that's what you pick for your unit. Okay. What else? What else? Good stuff. I mean, because that's what we need to do. We need to see where you having questions, where you having problems.
Was e to the x plus 3 to the x?
3 to the x.
Yeah. That just the normal one?
Was this from the website?
Yeah.
Yeah. Yeah, that's just your basic antiderivative. Now we haven't run into a 3 to the x very often, right? But what's the derivative rule for a 3 to the x? The derivative of 3 to the x is what? 3 to the x times ln, not ln x, ln 3. So the antiderivative, you don't times by ln 3, you times by 1 over ln 3. 1 over ln 3. So the antiderivative of this is just e to the x, and the antiderivative of this one is, it's on page 333. It's one of the ones on page 333. Now they write it as 3 to the x over ln 3, same thing, plus c, so that would be that one. So yes, you should know that. We haven't done very many of them, so it's probably not going to be very many of them on the gateway test. But that's just, so 2 to the x, 4 to the x, whatever, something else to the x.
X, C, and X.
And where'd you get that? Okay, was that one of them that I had said to do? Okay. Now, well, I probably should have been clear about that because I was just talking the same about that. 8.1, there's a lot of integration by parts ones we're not going to do. So 8.1's got a bunch of problems in there that we're not going to do. But on the assignment sheet, I listed a few. You know, if you look through here, 8.1, 8.1, 8.1, number 40, what number is that? Yeah, I don't have that down as well. Now, so what could happen in this section a lot, and Sam and I were working several over there, is you start with u substitution and then you end up with integration by parts, or you start with integration by parts and you end up with U substitution, kind of thing.
If you think change instead of this side to cosine, that makes it
No,
more-
actually, because you get a sine over a cosine square, which would be great if this x wasn't set.
Yeah.
Oh, I left it the way it is, and make that dv from the v is just c.
Right, and so the good recognition here would be, and it's actually not bad, is that this is algebra, this is trig. If you remember that the derivative of secant is secant tangent, right? So that means the antiderivative of secant tangent is secant. So this one actually works pretty nice. So here you would let your u be your x, and your dv would equal your secant, it's everything else, right? That's what we said, let it be everything else, because you got to account for everything. So this wouldn't be awful. It would be a little harder. It's definitely not one of what I said was the more basic ones, but it's close. But it requires you to know that the antiderivative of secant tangent is secant, which we should. I mean, that's a basic trig derivative rule in reverse. It's just not what we see that often. So this is just secant x, and then this is du equals dx, okay? So now we get u times v, so x secant x, minus the integral of v du, so it's secant x dx, like that. Okay, so there's the trouble right there, right? What's the...
I turned it from cosine and u substitution.
That doesn't really work though, because you don't have a sign, you don't...
That's all.
Yeah. So I think doing the antiderivative of secant is probably one of those where we would actually do integration by parts again. We would probably let that be the u, and then the dv just be the dx. So this might end up being one of those that kind of switches back and forth a little bit. So I probably would, yeah. So I wouldn't spend a lot of time in 8.1. I would do, if I was going to do some integration by parts ones, I showed you on the website, on that Jacksonville University website, they've got a couple of integration by parts in there. Now that first one, a lot of times, the first integration by parts in there was one you had to do twice, which I said we probably would do. The next one down there, I don't remember which one it was. And then I listed a few in 8.1 additional ones that wouldn't be bad to do, and I would stick with those, because otherwise you're going to get, again, I think one of the things I told you was the danger people run into is the gateway test is going to have one or two integration by parts ones, and all of a sudden you got 7 of them on there and you're doing integration by parts. So I grab somebody's paper and I go to grade it and I see U and DVs all over the place. And that you're not going to have that many of those. Okay, there's not that many of those. Sam was working like he was just kept doing section 8.1, 8.1. I said, Sam, quit spending so much time doing integration by parts. I mean, that's fine. They're going to be fairly basic ones. There's going to be way more U substitution. If you want to go here and you want to look at integration by parts in these tests, okay, this is one we said, oh, that's a U substitution. Let me see the integration by parts one. Right here, number 6, right? If you go through these Jacksonville practice tests and you go to problem number 6, a lot of the time in these is just a kind of a run-of-the-mill integration by parts that I would want you to do. I think this is the one. This would be an integration by parts you have to do twice because of that x squared. I would probably ignore that one. But here, number 6, that's just a really good integration by parts right there, right? That we would do. Now you might say, well, wait a minute, I thought x to the 8th doesn't mean you have to do it 8 times. No, it won't, because this one's with L and x. It's the ones that have e's and signs in them when you have x squared and stuff. You end up having to do multiple times. Okay. So number 6 on these Jacksonville ones are not bad practice for integration by parts. Those are a little more like what we're going to do. Okay. All right, and then that other website I showed you, the other website I showed you right here, I said there were 3 of them that you could look at right here, integration by parts. These first 3 are good ones to do with integration by parts. Those 3 right there are good practice. Okay. Alright, what else? Anything in the U substitution page, that 5.4,
X squared. I guess X squared e to the 2. I thought you already had to do it twice, right?
what'd you say, x squared e to the 2x?
That's
Yeah,
fine.
that's like one of those items, that's an integration by parts. Alright, turn to, well, I've got a few to do, but let's turn in the book. Okay, so you got the website, some places, and I've kind of emphasized where to begin. Turn to page 341. 341, because I think many of you ought to be spending some time before tomorrow on this page. Now, you can go into those practice tests, website's not bad, but the danger is picking some that aren't that great. This page is full, and I don't know how many of those you've done, but those would be great ones to be working on. Now, those are ones we're supposed to have been working on, 3-4 days ago. But I don't know. Look through that page. Look through page 341 there and see if there's something that jumps out at you that looks like something that you're not sure what you would do. 42. Anybody have a thought on 42?
Just let it be the inside.
Let you be the inside, right?
On 43, would you let you be like the
Not quite. No. You let u equal what?
Squared plus 2x.
The inside of the bottom. The inside of the bottom. Because that's x squared plus 3x plus 5, and what's the du of that? 2x plus 3 dx, which is setting right there on top. Right? Okay. Well, because maybe not everybody's seeing that. I actually want to look at 41 too. That's now that you guys talked about that other one. But okay, so you've got this, and you've got x squared plus 3x plus 5. I mean, let's don't get so hung up on some of these kind of more bizarre ones that we lose sight of the easy ones, right? I mean, the ones that should be easy ones. It should be an easy one. Okay? And we can get 8 out of 10 if we take care of those, right? We let u be the inside. The very obvious, we're looking, u substitution is the one, is way more important for us than integration by parts. Okay, the UDV is something we want to be able to do. We want to see, in some cases where that can work, but the vast majority are going to be basic antiderivatives or u substitution. So we let u be that, and it's because, and the reason it's going to be good is because the derivative, the du is going to be that. Well, that's setting right up there. So all of this in the red is just du. And then this is just what? U to the negative 4. Everything else is just u to the 4th on the bottom. U to the 4th on the bottom is u to the negative. It's not ln, right? Don't do that. Some people tend to do that on the test. You get u to the 4th, they think, oh, that's ln, u to the 4th. No. ln is only when it's u to the 1st down here, right? Because then you get u to the negative 1, you're trying to raise the power up to 0, divide by 0, you can't divide by 0, it doesn't work. So only when you have 1 over u is it ln. If it's a power, then it's a power. So we raise that up to negative 3, divide by negative 3, plus c, and then we put our u back in. Okay? Now, 41 does have something, and I've been kind of waiting for people to ask on this one. Okay? All right, what do you think? What are first thoughts? Just what comes to mind right away? Let u be the bottom, right? If you let u equal x squared plus 1, let's think ahead. What's the du? 2x dx. Now, do we have an x dx setting up there? Plus 4 is in the way. It's not x dx setting up there. It's x plus 4 dx. That's different. So it's a good thought, but we don't. What's the other thing you think of when you see x squared plus 1 down there? arctangent. Arctangent. But what's wrong with that? The x is in the way. If the 4 was the only thing there, we'd be okay. Well, do you see what we just said there? The two things we would normally do, one is let u be the bottom, but the 4 is in the way. The other thing we do is let u do an arctangent, but the x is in the way. What do you think of that? Is that legal? Is that legal? Now, we said you never split apart a denominator, right? Well, did I split the denominator? I did, right? So what I did is I split this apart. I said, let's put x over this plus 4 over this, right? That's legal. Now, usually we do it with a single denominator, like a u or an x or an x squared or something like that. But as long as we keep the x squared plus 1 together, we can split this into two integrals. We can take the x, and then we can take that one there. Okay? So what's this one over here? Well, that's just going to be 4 arctangent, right? I mean, this one's an easy one. That's just 4 arctangent. What are we going to do on this one? Let u equal the x squared plus 1, because that was Will's first thought, right? But we said, well, if you let u equal x squared plus 1, then the du is 2x dx, and there is an x dx setting there, so we put a 1/2 over here, and so we get x dx, and so that takes care of that. So this whole thing just ends up being 1 over u, and a 1/2 and a du out here, right? So what is that, just 1/2 ln? So 1/2 ln x squared plus 1, we don't even need the bars because the x squared plus 1 is a... So that's a tougher one because you had to recognize to do that. But think about the thought process, right? The thought process, you had good thoughts right away. You said let u equal x squared plus 1. That's a great first thought. But then you got to take it a step further. Then you say, okay, the du would be 2x dx. Do I have an x dx setting right there? I don't. That 4 is in the way. Then you think, well, it could be an arctangent. Well, that x is in the way. Oh, geez. Well, I wish I could split those apart so just the x or just the 4. Oh, it turns out you can't. You can't split them apart. Okay? Now, will I give you one like that? That'd be a hard one. That would be a hard one, but I certainly could give you this one individually. That's a pretty basic u substitution. And I can give you that one. That's just a very easy, just arctangent, right? So individually, they're not hard. The hard part was recognizing that we could split that apart and get it to be that. Okay, what else? Because like I said, you go to 8.1, a lot of those on that page we can't do. We're not going to do. Except for the few that I listed on here. You know, the LH packet, those have more. There's more in the LH packet we probably should be able to do. Okay, most of those we should be able to do. And this page 341, we should be able to do this whole thing. Okay, 58, you said? Okay, so 58 is tangent squared times cosecant. Okay? So what do you think of that one? What are some first thoughts? What?
You do integration by parts and let u equal...
No, because it's in section 5.4 and we would never, and they don't learn integration by parts till chapter 8. So no. It's not a mix, but why else? It's not a mixture of different function families. It's all trig. It doesn't look like these over here, right? X e to the x, x ln x, e to the x ln. It doesn't look like any of those so far. No. Tangents on the inside. So a thought might be let u equal tangent. Well, what's the d?
How is tangent on the inside?
What does tangent squared mean? Remember, that's lazy notation. Lazy notation. Tangent squared is lazy notation for this, right? So tangent's on the inside, and the derivative is secant squared, and that's not really said. I think I would change them into sines and cosines. You had that idea on an earlier one, and sometimes that's good. Now, the reason I didn't like it on that other one is because it was tangent and secant, and so you'd have sine over cosine times 1 over cosine, so nothing would cancel. Here we're going to have sines on top, and here we'll have sine on the bottom, and something cancels. So I think that is nicer. So this would be sine squared. So this would turn into sine squared over cosine squared times 1 over sine, right? So this sine would cancel one of those. So this thing turns into sine x over cosine squared x. And Emily, maybe it would be good every time you see a square to write it this way. If that's not obvious to you that that's on the inside, then I think you should probably stay away from that lazy notation and do this. Okay, I call it lazy notation, but I do it all the time. But it is lazy notation. It's just because we don't want to write all those parentheses and stuff. Okay? But if it causes us confusion, then it's bad notation to use. Okay, so now what would be the obvious choice? Now letting u be cosine is a great choice because the du is going to be negative sine so the negative I can move over to the other side here. Right? So my sine x dx would come out, would be a negative du. What else do I have in there? 1 over u squared. How do I want to write that though? I want to write that u to the negative 2. We don't want to write 1 over u squared because then we're going to think it's ln, and it's not ln. Okay, so we're going to raise that up 1 would be negative 1. Divide by negative 1 will cancel that, which is what, 1 over cosine plus c, or secant x plus c. So, good one. Good one. So sometimes changing them sines and cosines is a good thing. I mean, I think sometimes that's a good thing. Okay, especially if some things will cancel. Okay, or you could get a u substitution kind of thing. So changing a tangent to a sine and a cosine. Okay, and you understand why tangent squared is sine squared over cosine squared, because tangent squared is this, which is the same as this. And anytime you square a fraction, it's the same as squaring the top, squaring the bottom. Okay, so it's sine squared over cosine. Okay, what's another one? I mean, don't just randomly pick them. Look at something that you legitimately wonder about.
We'll go with 53, but we have to know the antiderivative of arc sine.
The antiderivative? No. But that's okay, because on 53 you don't have to do the antiderivative of arc sine. Because what are you going to let u equal? No. On 53, you're going to let u equal arc sine. Because what's the derivative of arc sine? You have to know the derivative of arc sine is what? 1 over, wasn't that what's setting right there? So that whole integral just substitutes into that, right? Because the arc sine would be the u on top, and then this, all the rest of it is the d. Yeah, so 53 just let u equal arc sine, the du is that, and then, so now you just got 1/2 u squared, so 1/2 arc sine squared is it. Okay? What about 50? What thought comes to mind when you look at 50? Comes to mind then. Can't split apart the bottom, and the top only has one thing. I mean, the one we did earlier, the reason we could split it apart is the top had two things. So we put this over the bottom, and then we put this over the bottom, right? There's only one thing, right?
Did you let U equal the bottom and then solve it for X?
That's right. That's what we'll do. Whenever, so you were on the right track, Emily. Like, I wish I could split this up, but only if this was flipped could I split it up. Well, what happens is if you let U equal the bottom, that's what happens a lot of the time when we let U equal the bottom, right? The bottom becomes our U. The du here would just be 1 dx, so that's just dx, so the dx is the same as du, and then we got this x squared. Well, we would solve this, so x would equal u plus 3, so this would be u plus 3 squared, right? Well, u plus 3 squared is u squared plus 6u plus 9 over u, and now we can split it apart. We might have done one very similar to it. But that's one of the reasons, so Scott, that's one like you and I talked about earlier, you were asking about. When do you let u be the bottom? This is one of those cases, you let u be the bottom, you solve for x, and then top it. Now you can, so what basically what happened is you flip this around. Emily was thinking of splitting it apart, but we can't because of the way the bottom is, but when we let u be the bottom, a lot of times we can split it apart. Okay, what else? Which one? 39. So we got the integral of x squared, and then instead of the square root, I'm going to write it as 1/2 power. So we have 4x cubed plus, what is that, 5? To the 1/2 power. So now, Skylar, it's a u substitution, right? I mean, it's stuff on the inside. Most of the ones on the test are going to be basic ones or u substitution. So you're thinking of those most of the time, okay? And the first thought with u substitution is something on the inside, right? So what is your thought for u there? Perfect. And the bonus, the real reason we want that, not only is it on the inside, is what's the du? It's going to be an x squared dx, and there's an x squared setting right there. So the du is going to be 12x squared dx. Yes, absolutely. Let's talk a lot about these, because these are the ones you're going to see more of. These are the ones we want to be able to do for sure. Now the 12's not up there, so we'll just move that over. And we got x squared dx. So now your x squared and your dx are just 1/12 du, same thing. And then that's all u to the 1/2. Right? Now let's make sure we do our fractions correctly. So we raise this up to a 3/2. And we divide by 3/2, well, that means you times by 2/3. So you're going to have a 2/3, and you've got a 1/12. Now, how does that work? Well, those would cancel. What is that, 1/18? 2 and 12. 1/18 u to the 3/2, which we would change into 1/18 4x cubed plus 5 to the 3/2 plus. Just be careful that you finish it up right. Now, a lot of times at the end, I don't finish it all the way through. But, I mean, we got to make sure we do that, right? Because that's, you make a mistake there, and then that's especially frustrating. One plus x to the 1/2. All to the what, 3rd power? And down here we got x to the 1/2. dx. First thoughts?
Make x, I mean 1 plus x.
The inside. Because the derivative of square root, remember, is a square root on the bottom. Because the derivative of 1x to the 1/2 is going to be x to the negative 1/2, and that's what's sitting right here. So it's going to be a nice, it's going to be a good, nice substitution. That's what I like about this page, is the vast majority of this page is pretty good u substitution. Maybe a tricky one here and there, but not too much. Okay? So the 2, I'll move that over there. But this is 1 over x to the 1/2 dx, and that's what we have. Let's get some color here. That's what that is. So that's going to be 2 du, and then this is u cubed, right? And again, that's the whole point. It turns it into stuff we do. So raise it up to 4, divide by 4, so that'd be 2/4, or 1/2 u to the 4th. And finish it. The only downside, now you have to go to your calculator probably to check them, or take a picture of the answer book. But again, good ones to practice, I think, would be that Jacksonville site. You know, there's u substitution there. There's, like I said, number 6 is a good. Number 6 on that Jacksonville, those tests, number 6 is a good. Looks like it's a good integration by part ones to do, very similar to what we're going to have to do. Okay, so I'll say it again here. You go to these tests. I mean, every test I picked seems to be the same. A good basic one. This one every single time seems to be an integrated by parts I wouldn't worry about, so I wouldn't worry about number 2. This is a good u substitution one. Number 4 we said is one we're not going to worry about. Actually, number 4 in this one actually ends up being halfway decent. You can let u be the inside. You got a z in there. So a lot of times 4 was one we weren't really going to mess with. Actually, maybe it was number 8. Number 8's the one in this one. Okay, so now just when I said it was number 6 every time, they've changed it up on me a little bit. This time it's number 7 is a good integration by parts. This is a good u substitution, just like u be the bottom, because you got that x dx in there. You're down to 18x dx down here. So that's going to be good. This is that arctan thing we were talking about, right? This is actually a better one. It's got the 1 plus, so this would definitely be one we could do. 8's the one we wouldn't want to do here, right? That's that partial fraction. Okay. So,
How come on the partial fraction ones, you can't just like FOIL?
well, you can foil it. Actually, they put it that way because it makes it better to do partial fractions. If you foil that, what would you do? I mean, you couldn't let u be anything. You could let u be the bottom, but the du's not sitting there. You know what I mean?
Yeah.
That it's just one of those where it just wouldn't work. I mean, yeah, there's just, it would be that to the -1, which you can't do because it's got stuff on the inside. It's just,
Multiply those like that? Like, did you do like the integral of 1 over x plus 2 multiplied by the 1 over x plus 3?
now, no. Because, well, no, because then why would we even need integration by parts? Because if you had this problem, we would just do the integral of x times the integral of that. You know what I mean? I mean, we can't. Yeah, we just can't. And why? I mean, it's just, and it's easy to check because if we try that, and why is that? Well, it goes back to this. It goes back to our derivative. Remember when we first learned the product rule, we said, okay, this is x to the 5th. We know the derivative of that is 5x to the 4th without that, right? Well, if you try to just do the derivative of each one of those individually, right, you get 6x cubed, which clearly is not 5x to the 4th. So it doesn't work. And so likewise, we can easily prove that the other way, that we can't just multiply. We have a sum rule for integrals and derivatives and a subtraction rule. Then that's why we can split apart. So number 1 up here, right? That's why we can split this into 2 integrals. We can just do those individually if it's plus or minus. But if it's multiply or divide, you can't do it. All right, let's pull up some practice ones. You guys have watched me, and I know what happens. Everybody gets all confident, like, oh, yeah, I get it. Well, yes, if I was doing the gateway test for you, you would be in pretty good shape. Okay, but since I'm not, why don't we let you practice them? Because at any point along there, if you did something different than I was doing, you would be in trouble. So, let's try those. Exactly. There you go.
I don't even study.
All right. Well, but what you got to keep in mind is we go slower than college calculus, right? So
No, we don't. We do
Wait,
Calc
so
2.
basically if you're
What?
not taking,
Well, we do Calc 2.
We get into a little bit of Calc 2, but I'm saying we've got a lot more time to spend on it than you do in college.
if you're, so if
So
you're not
if this,
taking-
if you're telling them this class is way too hard to take in high school, it's gonna be harder in college, because it's faster and it's,
So if you don't take
if you
the
don't take
test, the only reason to take this is just to get a
Practice for-
feel for it.
well, not, and you don't have to take the AP test. I guess I can record this, but you don't have to take the AP test. Now, we're gonna actually, in the next couple weeks, we'll talk more about the AP test. There's two reasons, there are two ways you can skip in college right to Calc 2, right? One is to take the AP test, right? Take the AP. The only reason to take the AP test is you can get credit for Calc 1 and you can jump right to Calc 2. However, most schools, including UNK, UNL, will just let you skip the Calc 2 anyway, without the test. You just tell them, I took Calc in high school, I want to start in Calc 2, and they'll let you.
I really want to take it.
Now, so those are options. I would say if you have an A, maybe if you have a B, that's a good option. Skip right to Calc 2, okay? Because you'll be bored to death in Calc 1 because it just, I have students come back, and I've told you this, I've had students come back and say, oh yeah, I did Calc 1, I took Calc 1, it was easy, and you're a great teacher because, it was so easy for me. And I thought, well, thank you for telling me I'm a great teacher, but you took it again. If you took Algebra 2 twice, would it be pretty easy the second time? I hope so, right? I hope it would be, right? I mean, so I appreciate the nice words that people will tell me on that, but that's okay, right? I'm okay with you do that. So if you've got a B, maybe if you got a B, if you got a C or below, you would probably feel more comfortable going to Calc 1 again, right? But understand, that's what you'll be doing. You'll be basically taking Calc 1 again, which is fine. It's nice to start college with a class that you're comfortable in and you're familiar with and whatever. And you're going to be in it with a lot of students that didn't take Calc at all in high school, and so they're going to be scrambling because it's going to be really fast, and they're going to, and you're going to feel pretty good because you're going to be like, I've seen this before, I can do it, And that's fine. There's nothing wrong with it. But understand that if you have a pretty good feeling about how things are going and how you've done, taking Calc 1 again in college will be literally just repeating, what we've already done. So, but those are your options. But again, so if you're a junior and you're thinking of these kids over there and they're thinking, boy, I've heard Calc's hard, I don't want to take it. Well, if you're going to have to take it sometime, you're a lot better off taking it now and maybe struggling and whatever. But then when you go to college, and that, then it'll be that much easier. And that's the other thing I've said about dropping it at the end of this term, because fourth term, we spend a lot of time reviewing and we do those packets and we go back and all the stuff you learn and get it, repeat and hear again and review in the packets just helps you if you have to take Calc in college. So if you have to take Calc in college, I think you should stick with it all the way through the end of this year, just because everything you see and hear the rest of the way is going to help you if you have to start with Calc.
How do you know how far you need to go, in college, math-wise for your degree?
Well, it depends. I mean, you probably get on college websites, look at the courses of study and stuff. You can find all that information online. Yeah, college advisors and stuff like that. I mean, when you're going to sign up for classes, especially, but you're saying even now as a junior, if you're not.
When you look at majors, they'll pay you the credit departments on.
But you can go on websites and you can find that information. Okay, any questions on this right here? What about it?
I typed in my calculator, I got 5.6, and I did not get 5.6.
Now, I didn't finish this, but I would want you to finish this.
Yeah.
I don't, when you should type in the calculator, right? Because this, I don't know. This would be, what, 37 and a half?
5.6.
This would be 0.6, so this would be 38.1. And this would be 13 and a half plus 1. This would be 14.5.
Did you type in the original integral or the
Yeah.
one?
What is it like 23.6?
Yeah, it's
23.6 is what it should be. Did you type in the original on your calculator to check it? I don't know.
Let me see. Let me see.
Here's number 3. Now there's no LNs in any of those, right? There was no LNs because everything was 1 over something squared or 1 over, like this one. So it's not an LN, right? So u to the -2, raise that up to -1. Now notice I changed these numbers. We talked about that. I plugged my 0 and my 2 into here and got 4 and 28. Or you can go back to your A's. You can go back to your original letters and use the 0 and 2. Doesn't matter. It's going to be the same either way, right? You can stop here with the U's and take your 0 and 2 and plug them in there. Or you can go back to your A's like we normally do, and you can put your 0 and 2 into that. Okay, now that was kind of a bizarre one, kind of weird fractions. I wouldn't worry too much about those, but you might. I mean, they're not going to be a ton of definite integrals anyway. Most of them are be indefinite integrals. Most of them are going to be plus C at the end, right? But then you're going to get that. Okay? All right, let's go.
Are you still doing 5.6?
I hit X squared. It's X cubed.
So it was right. It was 23.6. Okay, here's 3 more.
Actually, just put 4.
4x sine 2x minus a plus 2 cosine 2x minus a plus c.
Oh, we got that. Do integration of the parts.
Would you use cosine to
4x sine 2x minus a plus 4 cosine.
I got plus 2 cosines, because you have to kick out
Yep.
that 1/2.
So what would you use u as cosine 2x minus a?
No, u is 8x, because algebra,
Oh,
and dv is cosine 2x minus 8. x.
I just, yeah, you just let, u equals tangent, it's just.
No, it's negative.
You don't need that, no, just let u equals tangent, and then you get that the derivative of tangent secant squared, so you get 1 over u squared. Wait, and then you get arctangent of tangent, which is just x, isn't it? Is arctangent of tangent just x? Or is that the other way around?
Say that again.
Is arctangent of tangent, so like you have.
Just x, well, yeah. Tangent of arctangent. Tangent of arctangent would always just be x.
But what about arctangent?
Arctangent of tangent,
Is different, right? So,
kind of like square root of x squared, might not be x, it'd be the absolute value of x.
so we just
Is that what we're
Is that what you end up with there?
on
So,
5,
yeah.
I got arctangent.
It would be safe to just put x. I would not count that wrong. But I think you're right, that is what's happening. 5's, what's that?
The sixth one you could split apart? Like into the plot, like the integral of x
Yes.
squared over x dx plus the integral of negative 1/3 dx.
Say that again now.
Because if you had, can you put the x squared over the x and the 1 over the 3?
No.
So
Never
is
split
there-
the denominator. Never split the denominator.
So on that one, did we only have a single denominator?
No, on that one we put x squared over the x minus 3, and we put 1
Oh, so
over
you
the
could
x
put
minus 3.
X squared over x minus 3 and 1 over x minus 3.
Right. But you never split the denominator.
Is this the one we did? Is 6 the one like that we did earlier?
It's similar to that, yes.
But then when you
So I think Emily's got the right idea there.
so then when you have,
Although you wouldn't have to do that though. You could just let u be the bottom. If you just let u be the x minus 3, then you could solve for x and plug it in and then FOIL out the top, and then it could be when you could split. So that's probably how I
you
would
split
sit.
up the x squared and x minus 3, then can you split that into x? No, you can't split
No, you can't split it up. So that's what I'm saying. So if you split that apart, you're going to have x squared over x minus 3. You're still going to have to let u be the bottom. And then you're going to have to solve for x, right? Either way, you're going to do that. And then the plus 1 is so to me, I would just let u be the bottom. I would just let u be the bottom and then solve for x and plug that in.
Do you just leave that plus 1? It just stays.
What's that?
Does that plus 1 just stay there?
Yeah.
Just for the x?
But then you're going to FOIL that. So
and then you can split up.
Right, so you got u squared plus 6u plus 9 plus 1, so 9 plus 1 is 10.
Okay.
You're done with 6, just. Yeah,
Did you get 1/2 u squared plus 6u plus 10ln?
I put my x's back in.
Yeah, but is that what you, that's not what you want.
It's kind of similar. I could be wrong, because I did mine differently, like you said to do it.
Now, 5 is kind of a weird one, kind of a trick one a little bit, because actually what's 1 plus tangent squared? Secant squared. And secant squared over secant squared is 1.
It's just x.
So the antiderivative of 1 is x plus c. But if you let u be, what did you let u be? Tangent. Then you get tangent of arctangent, tangent, right? Which is just x, so it works out the same.
Yeah, Jesse said, asked if that was an identity.
It is. But sometimes I don't think of that either. But let u be tangent's a good idea, because then you get 1 plus u squared there, and the du is secant squared. So here, let's. Now, what'd you do on 4?
We did a,
That's the integration by parts, right? I mean, that's the classic integration by parts. It's an x times a trig, right? It's an x times a trig. Now, there's a 2 in there. The -8 doesn't really do anything. That's no big deal. So you got algebra, you got trig, the du. You got to do the antiderivative, so you got to remember to kick out 1/2 because of that 2. But other than that, and so it's u times v, and then you just end up with this. So again, you're going to have to kick out 1/2 again. So the antiderivative sign is negative cosine, so that negative turns to a positive. And then you kick out 1/2, so 1/2 times 4 is just 2. So that's kind of a basic one there. Okay, it's a little tricky though because of the 1/2 and kicking those out and everything, and so you gotta kind of be careful there. And then when you take u times v, that 8 times that 1/2, that's why that's a 4 out there. Okay, 5 we said was that tricky one. I just wrote arctangent tangent, but it would just be x. I would be okay if you just left it arctan of tan x. If you had done it this way, I'd probably let that one slide. But
So-
okay, huh?
So that one's just x plus c.
X plus c would be that one. And then this is the one we were just talking about, so we let u be the bottom, and then we solve for x, so u plus 3 squared, so that's u squared plus 6u plus 10, because it'd be plus 9 plus 1, okay, plus 10 over u. And now, I did the classic mistake here, then I forgot to put the x's back in, so I'm going to remind you during the gateway, hey, make sure you go back to x's, make sure you put your plus c on, so you split apart u squared over u, 6, 10 over u is an ln, but you do want to put your x minus 3 back in. So 1/2 x minus 3 squared, 6 times x minus 3, no need to distribute that easily. And then 10 ln, and then put x minus 3 inside the percent.
If we did distribute it and just got rid of the number, would you count off?
No, that's fine. All right, whoops, wrong way. All right, just got 2 more on here. This is just a stray mark again right here, this thing, so just ignore that, let it be x. What that was.